Go for it, Alex.
So the upcoming face-to-face test says it's on chapters 3 through 7, I believe. But the
It did. I
only
just erased it, but yeah, it did.
Oh, okay. It is just 3 to 4 to confirm, right?
It's actually through six. It's through chapter six. So what you might notice if you look in the practice test, one, I've moved the test. I've let your lab instructor know you were supposed to take it tomorrow during lab, but I let your lab instructor know yesterday that I decided to let you guys take it this weekend, and that means you can take it on Saturday, or you can take it on Sunday, or you can take it on Monday. But you got to take it in between, basically just after midnight Friday night and just before
Oh, okay.
midnight
So it's
Tuesday morning. Yeah,
it's another online proctored.
yeah. Respondus with lockdown browser and Respondus monitor and webcam.
Okay, sounds good. Thank you
Yeah,
for
I just did
clarifying.
that because I couldn't fit in the chapters in time. So, also, what you'll notice is the practice test. I took out that practice test that said 1 through 7. That one's just
Yeah.
disappeared. Now, the practice test that was before that was just supposed to be for online test 3, I think it was. Now it says online test 3 and F2FT02. So, it's also for the face-to-face test for this weekend.
All right, perfect. Thank you.
Yep. Good question. See, everybody's got the same question, Shania. Zane, Ashton, do y'all have any questions?
Yeah, it seems everyone had the same question about the face.
Yeah, that's always the scary part.
I have a quick question about the like for our scrap paper for the test.
Yeah, go for it, Zane.
So
What's up?
we're supposed to just to clarify, we're supposed to like show it on the screen, right?
Yeah,
Like front and back, or you're supposed to take screenshots during the proctor time.
yeah. Let me give you a full discussion so you'll understand, and this is going to be on the video, so it'll help everybody. But basically, what you're
Okay.
supposed to do initially is you open up your lockdown browser first, and then you sign into Canvas, and
Right.
that also requires you to do your lockdown respondus monitor as well. So that uses your webcam. There will be an
Right.
instruction that tells you to pan around the room. So you're supposed to take your
Hmm.
webcam at that time and show, everywhere that's reachable from your workstation. And
Right.
then on your workstation, you should have your all the paper that you're going to use that should be laid spread out on your desk so we
Right.
can see it. So you're going to scan the desktop, you're going to scan down where your feet are, around the table, everywhere you can actually reach, and then you're going to in one motion continue picking up each sheet of paper and showing the camera the whole front, flip it over, show the front camera the whole back, and do that for each page that you have laying on your desktop. And then you just start taking your test. And while you're taking your test, you're supposed to be, of course, writing down your work because I'm not going to at most, I'll give as 50% credit for getting the right answer if you don't show me any work, unless it explicitly says you don't have to show work. So you want to show all that work. And then at the end, you're supposed to then take photos by actually, it'll tell you in the respondus monitor situation, it'll tell you, but you're going to scan the front and back of each of the pages of work that you did, and then you're supposed to email them to me as as a single PDF within 15 to 20 minutes after submitting your final. I mean your exam.
Okay.
Does
Sounds
that
good.
make sense, Zane?
Yeah. Okay. Thank you.
Yeah, you are allowed, by the way, to have your own equation sheet. It just can't have any equations other than the ones that I said. You can't have sentences on it, stuff like that. But if you want a hard copy, because it's kind of a pain to scroll back and forth, if you go to, it's in the module called Helpful Documents and Links. If you scroll down, you'll see Allowed Equation Sheet and Other Test Information. That very top thing says 241 Calc Physics Allowed Equation Sheet. If you want to print that out and have that, that's the allowed equation sheet. So if you want to make up your own, you're welcome to do that. But if you do, it just like you said, like I said, you're gonna have to show it to me front and back. And if I find that it is different from the equations that I have on there, then that's cheating. So we just don't want to do that.
Okay. Sounds good.
Okay. Thanks for letting me answer that because I really wanted to say that to everybody anyway, so that helps. All right, looks like we had some more people come in, and it's now 5:30. Everybody can chat me your first and last name if you haven't done so already, just so I can have a roll attendant sort of thing. In case anybody has any questions about this, a couple people have already asked. I decided instead of you taking your test with your lab instructor tomorrow, and your lab instructor, by the way, might just tell you you don't even have to attend lab. That's completely up to him. And I let him know that yesterday. So you might already have an email from him, or you might get one real soon. So make sure you check with him and find out whether or not you actually have to attend lab. He might still have a lab thing that you're supposed to do, but he might let you off. But instead of you taking the face-to-face test there tomorrow, I decided to allow you to take it either Saturday, Sunday, or Monday using Respondus Lockdown Browser and Respondus Monitor. I have some students that were unable to use Respondus Monitor or Respondus Lockdown Browser, or maybe they didn't have a webcam. A couple of students just about every semester can't do that. If that's your case, then you can contact the testing center at whichever TCC campus you want and just try to fit in an appointment on Saturday or Monday. I don't think they offer anything on Sundays, but I do know they offer Saturdays on some campuses, and Sunday should be at one. But you need to make a reservation, and you need to do that immediately. So make sure you get that done so that you can take it. Otherwise, there might be some other way, but you're going to have to contact me if you don't have a ability to take it with Respondus Lockdown Browser, Respondus Monitor, and a webcam. So that's what our test is going to be. It has to be taken sometime after midnight Friday night, which would put it into Saturday, and sometime before midnight on two, or I should say, uh, 12:01 a.m. on Tuesday. It's got to be done before that. Okay, so make sure you get it done in that time frame, and it might vary a little bit from one person to the next. But either way, y'all don't want to talk to other people about it, because if you take the test first, say, and then talk to someone else that hasn't taken it, you're giving them an unfair advantage, and that is going to negatively reflect on you, because if there's any curve, the better a student does, the less likely the curve will happen. So just make sure you don't do that. And I just finished explaining, so you can check this out at the beginning of the video if you weren't here when it happened. But I just finished explaining my reasoning and what you have to do with the camera when you first start taking the Respondus lockdown browser Respondus monitor test. I also said that you are allowed to use your own equation sheet, but it's not allowed to have any equations other than the ones that are on my equation sheet. So if you just want to print out a copy of my equation sheet, you're welcome to do that. My equation sheet is in the module that says helpful documents and links. You scroll down and it'll say test stuff or whatever, and it says 241 Calc Physics Allowed Equation Sheet. That's the sheet you're allowed to bring. You should have, when you start that video process to take the test, you should have all of your paper. That means any blank paper you're planning on using and any equation sheets you're planning on using, they should all be laid out on your desk so that we can see how many of them there are. And then when you're doing the panning around and everything, you're supposed to then film front and back of every one of those pages. And then at the end, you're going to film front and back of all your work pages. And then you have about 15 to 20 minutes to email me a PDF of all those pictures of front and back of all your work pages. And I have to check them to make sure they match what I saw in the video. So make sure you make it crystal clear. You want to try to hold the paper as close to the camera as possible so that I can see every part of every page that you show me. All of that stuff, if any of that stuff doesn't work, like you don't show me the details of the pages, or if you're doing something weird, like I constantly see you working down below the desk where I can't see anything, i.e., it looks like you might be using an iPad or a telephone or something like that. I'll just have to rule that actual test was not a good test, and you'll have to remake the test, and you have to retake it. You don't want to do that. So make sure you sort of keep your eyes on the page, on the desktop, looking between the computer screen and the paper on top of the desk. If I see you doing much looking off to the side, or if I hear voices from other people in the room talking to you, that kind of thing, all of those things are reasons for me to say, no, this wasn't a secure test, and I have to make you retake it. So just do your best not to do that. I haven't had to do that with anybody. I did have some people that didn't follow the instructions, and they ended up, in some cases, the students ended up dropping or getting dropped. In other cases, the students took an F for the test or that sort of thing. But generally speaking, none of that ever happens. It's just, once in a blue moon. Anybody have any questions before we get started? All right. Well, it's 5:35, so we're a little later starting than I had wanted. But as I was telling you, if you look in your helpful documents and links module in Canvas, you will see allowed equation sheet and other test information. And that top thing, 241 underscore calc physics underscore allowed equation sheet, that's the allowed equation sheet. There is, as far as I know, one typo on it, and you're, of course, welcome to fix that typo if you find it. If I remember correctly, it was Kepler's third law equation. So you might want to check that out and fix it. But other than that, that's the only thing I know of. You will, as I said, have to show me all that stuff. But we're starting today. We finished chapter 6 last time. I didn't get into a full discussion of general relativity like I'd wanted to, but I did put that at the end of the video I made last night. So if anybody wants to hear a little bit about general relativity as opposed to just taking what the book has, you can scroll to the last maybe 10, 15 minutes of the video from last night, which is called something. Actually, let me tell you what the title is. The title is Newton's Gravity, Kepler's Laws, and a Sample of General Relativity. So that's the video that I posted on my YouTube channel. And if you want to watch the end of that, you can catch the intro to general relativity that I did for that class. It's not a mathematical one. It's just giving you an idea of some of the flavor of the history of the time, some of the things that astounded the public, some of the things that the press wrote, some of the things that Einstein said. But more specifically, it gives you Einstein's interpretation of gravity as not a force, but as a pucker in space-time. So you can check that out. Now that we've said all that, I'll let you know we are going into chapter 7, and chapter 7 is called Work and Energy. And as always, you want to open up with the chapter opening question and answer that question and read everything. And then we're going to go into the sections. The subsections of chapter 7 are 7.1, work done by a constant force, 7.2, scalar product of two vectors, which is what we also call the dot product, by the way. 7.3 is work done by a varying force. 7.4 is kinetic energy and the work energy principle. So that's really what we're doing in this chapter. And I'm going to go ahead and share my computer screen with you. Or actually, I'm going to share my iPad screen with you to motivate the idea of what work is and to help you see from examples how to work these types of problems. So let me go ahead and share my screen with you folks. Anybody have any questions before I get started? Reiterate that you should chat me your first and last name if you haven't done so already, just so I have that listed as you being here. Okay, so now it's up there. I'm gonna put my window here and I'm going to open up chat screen in case anybody has any questions. So if you think about work as it's used in everyday language, you would probably find some similarities between it and the definition of work that we use in physics. And that's sort of the nature of the words that we use in physics is they bear some resemblance to something in everyday life. That's why we use those names. But I want to sort of sift out so that you know the difference, sift out the very differences between work in everyday life and work in physics. So, for instance, if you take a job like mowing the grass, you would say, okay, mowing the grass is hard work. That might be a good way of starting it. And what I want you to think about is what is work in terms of physics. So if you think about a big lot of land or a big plot of land, if you will. I'm going to draw a rectangle just to give you an idea of what I'm talking about. So let's say that by that by that by that. Let's say this is a lot, and let's say you're going to mow this grass, okay? And let's say you have maybe this lot is 80 feet wide and maybe it is 10, 20, or 20, 40, 60, 80, 100, 120, 140, 160. So it's about 180 by 160 feet. Okay. Now, if you used a lawnmower whose blades were, let's say, 26 inches roughly, 24 inches is what I'm shooting for, but you always have to overlap a little bit. But if you imagine that you're allowing that overlap so that you cut basically a 2 foot wide swath each time, then what you would see is that since it's 2 feet wide, you would have to actually make a trip up that's 2 feet wide, and then a trip back that's 2 feet wide, and then a trip up that's 2 feet wide, and then a trip back that's 2 feet wide. And of course, that would make 40 trips at 24 inches wide and 160 feet long. So that would be, in some sense, a measure of the work that you would have to do. You can see that you just keep going on like that and like that. And once you did those 40 passes forward, backwards, forward, backwards, forwards, backwards, each one of those forward counting as one, backwards counting as a second, forward counting as a third, so on and so forth, then you might consider that to be some work. Now, if you had to mow again a slightly bigger lot, let's say you mowed instead a lot that was also 160 feet deep or long, if you will, depending on how you want to use the word, okay, then this could be one of the lots, but instead of it being 80 feet wide, maybe it's 160 feet wide. So that would make it roughly like this. And of course, it's not exactly the scale in this drawing, but I'm trying to make it to scale for the squares on the paper. So I'm going to say that this is 160 by 160. And I would suspect that every one of you would say mowing the lawn on the left is less work than mowing the lawn on the right. And in fact, what you'd see is mowing the lawn on the right would actually be 80 trips at 24 inches wide and 160 feet long. Oops. Evidently I wrote log instead of long. So that is a assessment, if you will, of the quote unquote work done in mowing the grass. And in fact, what I would argue is, uh, let's call this lot A, and let's call this lot B. I would argue that lot A takes, or let's see, I'm going to say lot B instead. I would say lot B takes slash requires twice as much work to mow as lot A. And I would base that on the idea that basically I had to take a 160-foot walk and then turn around, take a 160-foot walk, and then turn around, take a 160-foot walk. And I had to do that 40 times on lot A. But in lot B, I had to do that same walk, but instead of doing it 40 times, I had to do it 80 times. And if you think about it that way, then you might say, well, maybe just maybe, work is dependent on distance. So we could say work is directly proportional to the distance, meaning when I had to walk twice as far, which by the way is 80 times 160 feet. So 80 walks at 160 foot each gives you the total amount of distance I had to walk. And that's literally twice as far as 80 times or as 40 times 160 feet. So, in that sense, we've reached a conclusion that work, W, is directly proportional to distance. And that's what that little fish looking symbol is. That means proportional to. Now, the other thing is, what if I had two identical lots, let's say two lots like lot A, and in one case, I'm going to cut it with a really, really heavy 24-inch old-timey lawnmower that was required you to push it, and that pushing made the blades turn. So it wasn't even gas powered, but it was, basically twice as heavy. In other words, it took twice as much force because not only are you pushing it to move the wheels ahead, you're pushing it so that you can go fast enough to make the blades turn fast enough to actually cut the grass. If you look at it that way, then you'd probably say, okay, mowing lot A with the 20-inch gas-powered lawnmower was less work than it was with the 20-inch non-gas lawnmower, and that's because work is also proportional to the force that you have to apply. So by applying twice the force to the lawnmower, which is what's required by the manual lawnmower, you would expect that to be twice as much work for that reason as well. So from that, this basic idea of work, I think it's somewhat reasonable to assume that work is directly proportional to distance traveled and the force applied in traveling that distance. And that's exactly what it is. In fact, we go a little further and say, actually, work is equal to the constant force. So you assume, for instance, you push with some constant force. If that's the case, meaning it's a constant in magnitude and it's a constant in direction, then you're going to take that constant force and you're going to multiply that by the distance. But you're not just going to take that force, you're specifically going to take that component of force that's parallel to the distance. So I put those two little parallel lines as a subscript on the F. And that's really what matters. It's not what the total force you put into pushing the mower, it's what part of that total force that you put into pushing the mower is consistent with going a distance d. In other words, when I push on a mower, let's say you have a lawnmower like this. Here's a wheel, here's a wheel, here's the engine, here's the handle, and then when I push like this, then this force is made up of a y component of force that way and a x component of force that way. That red force is completely wasted because my goal is to push the lawnmower forward, which is parallel to that green part, and that's all that matters. So that's the real definition of work, at least in terms of a constant force at a constant direction. You take the magnitude of the force and you find the component of it that's parallel to the motion, which is what the green vector is, and then you multiply that component of the force times the distance, and that's the work done. So that's really what it is. Now, that doesn't allow for us to configure or to consider what happens if the force varies or what happens if the direction of the force varies. So we're not addressing that yet. We're going to introduce the dot product so that we can address that, and then we'll address that part. So right now, you have an idea that work is a quantity in physics that is force parallel to the distance traveled multiplied by the distance traveled. Because of that, we know that the units are dimensions for work are the units are dimensions for force times the units are dimensions for distance. And of course, that means that is a Newton times a meter in terms of in terms of units instead of dimensions. Okay, sorry about that. So when you see that a Newton times a meter is the unit of work, well, it turns out that we've actually defined another unit called the joule that is the Newton meter. So the Newton meter is a unit for the quantity work, but we use a different unit that's defined in terms of that, such that 1 joule is defined to be 1 Newton times 1 meter. So if you applied a force of 1 Newton, which is 1/4.45 parts of a pound, and you applied that over a distance of 1 meter, then that would be 1 joule. To give you an idea, if you picked up a really big succulent red delicious apple and you lifted it from the floor and put it up onto a kitchen table, well, that amount of work is about equal to 1 joule. So one red delicious apple brought lifted up from the ground and laid up to the top of a living room or dining room table, that is about 1 joule of work. So the joule spelled Joule, but abbreviated with a capital J. It was named after James Prescott Joule, who gave us the mechanical equivalent of energy. In other words, if you've ever had chemistry and you learned that 1 calorie is equal to 4.184 joules, that was James Prescott Joule that did that. And we'll talk about him later in 242. Just know that, for instance, part of the way they made their money was they made beer, and there's a beer in Great Britain called Jowls, and that's from their family. So that's kind of an interesting little sidebar. So that's an idea about what work is and what the units of it are. I've even given you a rough estimate of about how much energy is. And by the way, this is work, which is equivalent to energy. So what we'll learn is this unit of the joule is not only a unit of work, but it's also a unit of energy, so that work and energy are things that are somewhat interchangeable. I often will say work is or I'll say energy is anything that has energy is a thing that has the ability to do work. And then work is basically anything that can be done by applying a force through a distance. So for instance, driving a nail is something that requires work, because not only do you have to hit a nail like with a hammer or something like that, but you have to hit that nail through some distance. And if you want to, make sure you don't skip any cases, then you might even have to consider the case of pounding a very, very microscopic nail into hot butter or something like that, so that you can see it is actually work, even though it's such a small amount of force. But that's a way of thinking about it. Energy is the ability to do work, and work is applying a distance force over a distance, and specifically, it's the product of the component of force parallel to the distance times the distance. And if that force is varying, I'm going to have to teach you something else about doing that. So now that we have that little background on what force is, I'm going to work an example 7.1, and here we go. As always, it's good if you actually have your ebook open so you can deal with this, and make sure I'm recording all this. Yes, I am recording all this. Just want to make sure. So it says a person pulls a 50-kilogram crate 40 meters along a horizontal floor by a constant force FP equals 100 newtons, which acts at a 37-degree angle as shown in figure 7-3. The floor is rough and exerts a friction force, F friction, equal to 50 newtons. Determine A, the work done by each force acting on the crate, and B, the net work done on the crate. So let me write down the information they gave us. We know that the mass of the crate, M, is 50 kilograms. I'm going to make all this into 3 sig figs, so that's 50 kilograms, and it is pulled along 40 meters along a horizontal floor. So that means our distance, D, is going to be 40. And again, I'm going to add an extra digit, so I'd have 3 sig figs. So that's 40 meters is the distance traveled by a constant force, FP, whose magnitude is equal to 100 point newtons. And of course, putting that decimal point there means that that's now definitely 3 sig figs, and it acts at an angle theta. So I'm going to say theta is equal to, and in this case, I know they're using 37, but again, this is a case where they're really supposed to be using the equivalent of the 3-4-5 triangle. So I'm going to say this is 36.8 degrees, because that's closer to what they meant when they were doing 37 degrees. Only by me increasing it to 3 sig figs, it would be smarter for me to call it 36.8 degrees. That's what I'm doing. The floor is rough and exerts a friction force. Your book is calling that F sub FR. I don't do that. I just call it script F, and the friction force is going to be 50.0 newtons, again adding an extra sig fig. And A, the work done, is what we're supposed to be determining. So determine A, the work done by each force acting on the crate. So A, we want the work done by FP We want the work done by the friction force. We want the work done by the normal force, which I'll call Fn. And we want the work done by the gravitational force, which is the weight W. So I'll say W sub W is equal to question mark. And that's the four works that we want to calculate. And then B, we want to know the net work. So W net is equal to question mark. That's what we're trying to solve. Now let's draw a diagram and then a free body diagram so you can get an idea of what we're actually trying to accomplish here. So here's our crate. And what we're imagining is this crate is having a force applied to it. And that force applied to the crate is 100 newtons at 36.8 degrees, like that. And I'll draw a little break in the line right there, but what we're supposed to do is move this a distance of 40.0 meters to here, like that. Okay, so that's really what we're trying to do here. Now, the free body diagram for this, as we should always do when we're dealing with Newton's second law, you should draw a free body diagram so that you can actually pick out all the parts of the forces and stuff of that sort. So right now I have this blue force acting diagonally upward that is 100.0 newtons at 36.8 degrees. I also have a normal force which is acting in the positive y direction, and that's F sub n. And I have the weight, which is mg, pointing down. Of course, the mass, we're just treating it like a point object, and its mass is m. Now, in addition to that, we do have a friction force. We're pulling the box to the right, so the friction force must be acting to the left, and that friction force is F is equal to 50.0 newtons. Make sure that decimal's in there. And mg, of course, is 50 kilograms times 9.8. So I'm going to go ahead and turn my calculator on. If that would ever work, that would be great. So 50 times 9.8 gives me 49.00 newtons is that force. Now, in addition to that, I have to break that blue vector up into components parallel to the x and y axes. And what I can see is the x component is going to be positive, pointing to the right, and the y component is also going to be positive, pointing up. And in fact, if you look at the 3, 4, 5 triangle, the 3, 4, 5 triangle is like this. This is 3, this is 4, this is 5. Obviously not to scale, but this angle right here would be 51.8, somewhere around there. 50, I think it's 51.8, somewhere around there. And this one over here is 36.8. It's actually like 51.2 or something. We don't need that number so much, so I'm going to erase it, but the 36.8 we do need. And the main thing is to remember the 36.8 is opposite the smaller side. So that's why I have it up there in that corner instead of this corner. That being said, let me change it around so we can match it to the existing diagram a little better. So let me do this. I'm going to get rid of that. Let's say this side is 3, and that looks more to scale anyways. And this side 4, and this is 36.8 degrees. From that, you can see that the sine of 36.8 degrees is equal to opposite over hypotenuse, which is 3/5, which equals 0.60, and cosine of 36.8 degrees is equal to adjacent over hypotenuse. That's 4/5, which is of course equal to 0.80. And actually it's to any number of sig figs. It's literally 0.8000 and it's 0.60000 or whatever. So with that in mind, we can now go back and look and realize that if I want the y component of FP, which is the 100 Newton force, then I would multiply the 100 newtons times the sine of 36.8, and the sine of 36.8 is 3/5. So if I multiply 100 times 3/5, 100 divided by 5 is 20, and then 3 times 5, or 3 times 20 is 60. So that means this side is going to be 60.0 newtons. And if you want to find out the x component, that's going to be the cosine of 36.8 times 100. So that's 4/5 times 100. 100 divided by 5 is 20. 4 times 20 is 80. So this is going to be 80.0 newtons that way. So again, you don't have to do it that way. You can just throw it in your calculator or whatever, but that's why we keep using these triangles, so we don't have to do the math and use a calculator every time. Now, with that in mind, we can use this to determine what the normal force is, because in order to calculate the work done by the normal force, you need to know the normal force. And in order to calculate the work done by the weight, you need to know the weight force as well. So to do that, I'm going to say the summation of the forces in the y direction equals mass times acceleration in the y direction. And as often happens in this case, we're imagining the box sliding horizontally across the table, so the y coordinate's not going to change. That means the v in the y direction is 0, and it's going to stay 0, so that means the acceleration in the y direction is 0, and therefore we just get F n, well, actually, I'm going to use the line below it because it's more than just that one force. We've got Fn, which points up. And remember, the left-hand side of Newton's law is adding the forces, but if there's one that has a negative component, then I'm just going to subtract it, even though it's really addition. So Fn is pointing up, so that's positive. The 60 newtons is pointing up, so that's plus 60 newtons. And then the 49 is acting down, so that's minus 49.0 newtons. And that seems to be all of the forces acting in the y direction. Therefore, I can see that the normal force is actually going to be 49.0 newtons minus 60.0 newtons. And in fact, what we've learned here is that actually, this was, I think I did 5 times 9.8. That should be 490. 5 times 9.8 is 49. Yeah, 50 times 9.8 is 490. Sorry about that. Let's everybody go ahead and make that change real quick. It's really only a difference of the decimal place changing. Uh, I don't know why I said it was 49. I knew better. And therefore, this part becomes, instead of 49, it becomes 490. Oops. 490.0 newtons. And same thing with there. And I'm just going to erase this one. That way you know it's 490 newtons, and I'll put a decimal right here. That way we can remember that it's 3 sig figs. So I got 490 minus 60, which is 430 newtons, which is technically 430.0, even though the 0 is not a significant digit. So there's my summation of forces in the y direction, and that gives us a normal force, so we got that. Now I can also, of course, do the summation of forces in the x direction, but that would give us the acceleration, and we're not really worried about that right now. All we're really wanting to do is calculate the work done. So now I have all the forces. I know the friction force is 50 newtons. I know its direction. I know the FP force is 100 newtons, but that has a component that's 80 newtons parallel to the motion and 60 newtons is perpendicular to the motion. And I use the summation of forces in the y direction to compute the normal force, and the normal force turned out to be 430 newtons. So all I have to do is use solution work equals F parallel times D. That's really the formula that we're using here. And to do that, I'm going to say part A, the work done by FP is equal to. Now, you can either go ahead and just look at it and say, okay, the force that's parallel to the motion is the 80 newtons, so I could write in 80.0 newtons, and then multiply that by 40.0 meters, and that works fine. And we see 8 times 4 is 32, and then that means 3,200, so that's 3,200 newtons. And of course, we only had 3 sig figs, so that 0 there is not a sig fig, and that's Newton meters, which equals 3.20 times 10 to the third joules is the work done by the pulling force. Okay. Now you could have used something your book also has. Your book is calling this, instead of just F parallel times D, they also say it's F times G times the cosine of theta, where the theta is the angle between the D vector and the F vector when the D vector and F vector are tail to tail. Okay. That's the strict use of that. So if you wanted to do that one, what you'd see is the D vector, which I can draw right here. That's the D vector, and you see now that they're tail to tail. So the other way we could have done work FP, I'm going to write this in purple so you'll realize we're just doing it to show you another way. That's going to be 100.0 newtons times 40.0 meters times cosine, and now you see the cosine of the angle between them has to be the cosine of 36.8 degrees. And if you put that in, you go 100 times 40 times cosine 36.8, and that gives you 320 or 3.203 times 10 to the third joules. And of course that 3 there is not a sig fig, and that's also because we're going beyond the number of sig figs we're given. So there's 2 ways you could have done FP. I just wanted to make sure y'all knew that. We've now done the work done by FP. I'm going to go ahead and circle that or box it off, and that's W sub FP. Now I want to know the work done by friction, and this is kind of helpful to use the FD cosine theta formula for this one, so I'll use that for this one. So the work done by friction is equal to FD cosine theta, which in this case is the friction force, 50.0 newtons, times the distance, which is 40.0 meters, times the cosine of the angle between them. If you look at this, you realize that the friction force points this way and the D points that way, so the angle between them is 180 degrees. So we write this down as cosine 180 degrees, and of course the cosine of 180 is -1, so we end up getting 50 times 40 is 2,000, because 4 times 5 is 20, and then I got the other one, so this is 2,000 joules. And since the cosine is -1, that gives me -2,000 joules. And that is the work done by friction. Now, notice the work came out negative. If you find that the component that is quote unquote parallel slash anti-parallel to the displacement, if you find that component is actually anti-parallel, then you expect the work to be a negative. So that's us showing you that it came out to be a negative, and this is me telling you that that should make some sense, because obviously what was happening from the friction forces standpoint is the friction force was being completely overcome, and it was pulling one way despite going the opposite way. So whenever you see a force pulling one way and the object going the other way, you should expect that force to cause a work that's a negative quantity. So now I've got the work done against friction. The work done against the against the normal force is done as follows. So let's say W F normal is going to be, we figured out that the normal force was 430 newtons. We know that the distance is 40.0 meters, but in this case, we see that the angle between the normal force, which points this way, and the displacement that points this way, that's a 90-degree angle. So we end up getting 430 times 40 times the cosine of 90 degrees, and of course the cosine of 90 is 0, so the work done is 0 joules. equals the work done by the normal force. Now, that's also normal if you have a force that is exactly parallel, or excuse me, exactly perpendicular to the displacement. It can't do any work. The work done by a force perpendicular to the displacement is always going to be zero. That might give you an idea of what the work done by weight is. So let's calculate that. The work done by weight is going to be 490.0 newtons times 40.0 meters times the cosine of, in this case, you might actually call it negative 90, but either way, it doesn't really matter. Uh, Either way, you're going to get 0 joules is equal to the work done by the weight, and that's our work done by W. Any questions with that part so far? Whoa, I left my drink. No questions? All right. So now what we're asked to do is what is the net force or the net work? So for part B, W net equals the summation from I equal 1 to N of W sub I. In other words, you're just supposed to algebraically add up all the work that's done. In this case, we had 4 forces acting, and therefore we should have 4 different works being done. So I'm just going to add those up. And the way we add that is 3,200 joules minus 2,000 joules plus 0 joules plus 0 joules. All of that gives me a net of 1,200 joules. And that is W net, like that. And I box it off. And that should be the final answer. Anybody have any questions on that one? Now, interestingly, your book points out that you could do it this way, which is exactly what we did, where I said W net is the sum of the forces, but you could also say W net is the summation of F sub I from I equals 1 to N parallel times D. So that's actually another way of calculating it. You could take the net force instead of taking the net work. You could take the net force, multiply that by the displacement, making sure you take the component of the net force that's parallel to the displacement and do it that way. In that case, the components that are parallel are, we're going to say we had these 80 newtons, so 80.0 newtons, and then we also had minus 50.0 newtons because that is parallel, but it's actually anti-parallel, so that's why the negative is in there. And the other forces are just 0 when you're taking the components that are parallel. So you take that and you're going to say 80 minus 50 is 30, and then you're multiplying that by 40 zero point 0 meters, and lo and behold, you get 1,200 joules again. So that's another way that you could actually calculate the network done is you could take the net force and multiply or find its component parallel to the motion and then multiply that times the distance, and that would give you the network. Any questions on that one? All right, let's look at example 7.2 now. Make sure I got it. Yeah. Example 7.2. Example 7.2 says work on a backpack. Determine the work a hiker must do on a 15.0 kilogram backpack to carry it up a hill of height 10.0 meters. Excuse me. As shown in figure 7.4a, determine also B, the work done by gravity on the backpack, and C, the work done on the net work done on the backpack. For simplicity, assume the motion is smooth and at a constant velocity, i.e. the acceleration is 0. So let me write down the information that they gave us. For one thing, they gave us that the mass of the backpack was 15.0 kilograms, And that, of course, means that the weight of the backpack, which is equal to mg, is 15.0 kilograms times 9.80 meters per second. And that gives me 147.0 newtons is the weight. We were given that the height h is equal to 10.0 meters. And in part A, we're asked to determine the work a hiker must do. So for part A, we want to say work hiker, which we're just going to abbreviate as work H equals question mark. Okay, so that's part A. And then part B, the work done by gravity on the backpack. So for part B, we want to know the work done by gravity. So I'll call that W sub G. And then C, the net work done. So we want to know W net as well. Now our diagram is this. We basically have a person walking up an incline such that the height of this incline is h equal to 10.0 meters, like that. This is our displacement vector d. So that's the actual displacement that we're walking. And you can imagine, for instance, we have a person walking like this with a stick, and of course he's carrying a backpack. So swipe or no swiping backpack right there. All right, that's the actual trip that we're making here. And of course, we need to work out a free body diagram again for the backpack. So with a free body diagram, we might be able to draw our coordinate system like this and this. And what we see is we have a displacement vector, which generally you don't put on the free body diagram. So I'm just going to draw it kind of light just to keep you realizing that that's the d vector. But really, since we're talking about, for simplicity, assume the motion is smooth and at a constant velocity, that means that really they're not putting any forces horizontally, because if you put a force horizontally, then it would cause an acceleration. So what we're doing is sort of imagining that we're just putting enough force that it's free to move, and then like a single molecule is going to bounce off the back of the backpack, and that's going to make it move a micrometer, and then you wait another split second and another micrometer will move, and so on and so forth. So when you do that, what you see is we'll have the force that the hiker applies, which acts in the upward direction. So that's F sub H. And then we have the weight acting in the downward direction, and that is the 147.0 newtons, like that. And of course, we're supposed to not be accelerating. So again, we can say the summation forces in the y direction equals mass times acceleration in the y direction. But the acceleration in the y direction, as we assume the acceleration in all directions is zero. So in this case, what we end up getting is FH minus 147.0 newtons is equal to 0. So we see that FH is equal to 147.0 newtons. Now we have that. Now all we got to do is go ahead and calculate exactly what the work done by each of these forces is. So for part A, we'll do solution. And I will free up my writing a little bit. So not only is it okay to write this as F parallel times D, you could also write it as the component of D parallel to the force, like that, or you could go ahead and write it as F times D times the cosine of the angle between them. You just got to remember that when using this diagram, you have two vectors, a force vector and a displacement vector, and they're tail to tail, and this is the angle theta. That diagram goes along with the formula FD cosine theta. If you don't realize that that goes with that formula, then you could make mistakes. So now that we have that, I can go ahead and do part A. And part A asks us for the work done by the hiker. So the work done by the hiker is F hiker times D times cosine theta, like that. And of course, the work done by the hiker is the force of the hiker, which is 147.0 newtons. And then the D times the cosine theta, that actually is something by itself that's kind of helpful, because if you look at the diagram, you can imagine that theta is the angle specifically given in the diagram. So if I draw this triangle like this, we'd see that this is the angle theta that they're referring to. And in that case, that's a slightly, in fact, I shouldn't even call it theta. I should call it phi. Let's do that just because I'm not necessarily convinced that that's the angle between theta and I mean between FH and D. So that's the angle that the book gave us as theta, but I'm not sure that that's the formula that's right, because we have to have F and D tail to tail. So if I actually did draw F, what I would see is that F would be right here, and then you can see, oh, wait a second, this line is vertical and this line is vertical, so these two lines are parallel, and then this D is a transverse line, and we learned that when you have a line that traverses across two parallel lines, that alternate interior angles are equal. So what we see now is this is parallel and this is parallel, and that's the transverse, so this one's the interior angle, and this one are alternate interior angles. So that means, in fact, that this angle theta is the same as this angle theta. And now you can see that the theta we're talking about is the same theta that we defined for work. Okay, remember, work has to be the angle between the two vectors, force and displacement, when the two vectors are head or tail to tail. So we've now convinced ourselves of that. So now I can go ahead and do my calculation. The D is going to be, I think they told us the distance was, oh no, that's right. They told us the H was 10 meters. So if you take the sine of theta, uh, or excuse me, if you take the cosine of theta, cosine is equal to adjacent over hypotenuse. Well, the adjacent is the H and the hypotenuse is the D. So we see that H is actually equal to D cosine theta. So this D cosine theta is actually equal to the H that we were given, which is 10 meters. So now I can go ahead and write this as 10.0 meters. So this is 1,470 joules is the work done by the hiker. Okay. Any questions on that first part? So again, 1,470 joules is the work done by the hiker, and we work that out by F times D times cosine theta. But in this case, the D cosine theta turned out to be just H, so that made sense. Not only that, notice that by switching it to H, we see that the total force that the hiker applied, which is this direction, is exactly parallel to the height, which is this direction. Therefore, you could just take the force 147 and multiply it by the H, which is 10 meters, and that's why it came out to be exactly that anyways. Now what we got to do is the work done by gravity. The work done by gravity for part B is the weight times D times cosine of the angle between them, which maybe I'll call this theta prime because I haven't worked out the details of exactly what that is now. But I can go ahead and say that the work, or excuse me, the weight is 147.0 newtons. And then the D, in this case, notice the D is up this way. But if you take the component of D that's parallel or anti-parallel to H, or excuse me, to the force, which this is the force W, so the component of D that is parallel or anti-parallel to that is the H again. So you can see, oh, this is just like the previous problem where I've got a force acting this way and a displacement acting that way. So the angle between them really is 180. So in this case, I'm going to say 147 newtons times, let's put it back on pen, times 10.0 meters times the cosine of 180 degrees. And in this case, we're actually just seeing the vertical motion as the distance that we traveled. And with that in mind, we get negative 1470 joules is equal to the work done by gravity. Okay. So the work done by the hiker was 1,470 joules, and the work done by gravity was negative 1,470 joules. There's other ways you can do it as well. For instance, your book does it this way. Let me show you real quick what your book does. Your book says the WG is actually equal to mg because that's the force, and then it's multiplied by cosine or d cosine theta prime. And what your book does is says, wait a second, we know this friction force points down, or excuse me, this weight force points down, and the net displacement is upward. Therefore, we can put in here instead of d cosine theta, we can say it's equal to mg times negative d cosine just regular theta, because now it's getting basically by putting the negative in there, it's making them like they're actually parallel, and then you can see the angle from that. And then you also realize that this d cosine theta is h, so you end up getting negative mgh is what the work done by gravity is, and lo and behold, that's going to be negative 1,470 joules as well. So that's the way your book did it, and that's an acceptable way as well. So it's really a matter of there's a lot of different ways to solve any physics problem, and you have to learn all the individual techniques. But at the same time, when I ask you to calculate the work done, you just have to get the work done, and it doesn't matter which way you use, as long as you use a way that gives you the right answer. So now we've done the work done against by gravity. Now we're going to do the net work done. So we'll say part C, and that is W net is equal to the summation from I equals 1 to n of W sub I, where W sub I is each particular type of force that we encountered. In this case, the free body diagram showed us we really only had two forces. We had the force of the hiker and we had the force of gravity, which is the weight. So in this case, it's just 1,470 joules plus negative 1,470 joules, which equals 0.0 joules is equal to W net. And you might think, well, that's really weird because clearly the backpack was moved. Why was it not some net amount of work done? Well, it turns out moving an object from point A to point B is not necessarily indicative that a total amount of work was done. It turns out that there is something called the work energy theorem, and the work energy theorem says the net work done in any process is equal to the change in something called the kinetic energy. So we're going to cover that in a second, but the kinetic energy is 1/2 mv squared, and the change in kinetic energy would be 1/2 m parenthesis v final squared minus v initial squared close parenthesis. In this case, we said there was no acceleration, so we're moving this backpack infinitesimally slow like this, and when it took off, it was going 0, and when it got to the top, it was going 0, so the change in velocity is 0, so you get 1/2 m times parentheses 0 squared minus 0 squared, so you get that the network is in fact 0, which is exactly what this showed us. Anybody have any questions on that? There's a nice conceptual example that I'm going to do now, and this is conceptual example 7.3. So let me first off separate this with a nice neat line. So example 7.3, conceptual. And I normally don't write anything for the conceptual examples. I just basically go over it verbally, and that's probably what I'm going to do now. But I just wanted to write it down, and so we'd have some record of it. So it says conceptual example 7.3. Does the Earth do work on the moon? The moon revolves around the Earth in a nearly circular orbit. Excuse me. The moon revolves around the Earth in a nearly circular orbit with with approximately constant tangential speed, kept there by a gravitational force exerted by the Earth. Does gravity do A, positive work, B, negative work, or C, no work at all on the moon? So if you look at a picture of the moon orbiting the Earth, we can imagine that's our Earth. Well, our Earth just got quite a bit squished and elliptical there. And now I'm going to say this is the orbit of the moon. So that's supposed to be a circle. And it's supposed to be centered on the Earth. So that's pretty good. That'll be good enough. And what we see here is, for instance, the moon. Oops. The moon has a velocity, let's say this direction, and then it has a force pointing this direction. The velocity is this direction. And remember, the displacement is velocity times dt, the differential amount of time. So if I multiplied a small amount of time by the velocity, I would get a vector that points the same way as v. And in fact, I would see my displacement right there is D, and you can see that D and F are perpendicular to each other. Because they're perpendicular to each other and work is equal to F parallel to D, we can see that that's also F times D times the cosine of the angle between them. And in this case, the angle is 90 degrees, so the force is 0. So the amount of work that the force of gravity does on the moon, if you continue to go on the assumption that it is going at a constant speed in a circular orbit, is definitely that force is always perpendicular to the velocity and therefore always perpendicular to the displacement, and therefore the net work done is 0. Excuse me, is 0. Now, if the orbit was a little more elliptical, then there's going to be parts of the motion where the force of gravity is not only pulling, has a component perpendicular to the velocity, but it also has a component that's parallel to the velocity that slows it down at one end of the orbit and speeds it up on the other part of the orbit, and so on and so forth. So in that case, if it's an elliptical orbit, the friction or the gravitational force can actually do a little work because it has a component of force that would be parallel to the velocity, which is therefore parallel to the displacement. Anybody have any questions on that? All right, so this brings us to the scalar product or dot product of two vectors. Scalar product, oops, are, whoa, Nelly, are dot product. Okay, it's also called the inner product. That's another name that you might run into. You maybe get that in a linear algebra course or something along those lines. But the main thing is a product of two vectors. So it's sort of a machine that takes in two vectors and spits out a scalar quantity. And it was designed for a very specific purpose. But let me go ahead and explain to you the formula for it. So if you take a dot product of two vectors, I'm going to go ahead and underline this so we'll see what we're talking about. But if we take the dot product of two vectors, that would be written as A dot B. Well, it turns out that what we find most useful is if we define the dot product to be the magnitude of the vector A times the magnitude of the vector B times the cosine of the angle between them. So again, just like we did when we had the work formula, if you have a formula like A dot B equals AB cosine theta, which we can also write, by the way, as A times B times cosine theta. Just remember, if you write a vector as A with a little vector over top of it, that's the vector quantity. If you put it in absolute value bars or double absolute value bars, that's normally the terminology or the signs that we use to represent the magnitude. But also, if you just write the letter A without the vector symbol on top, that's also a symbol that we use for the magnitude of the vector. So, in doing that, either way, we have to realize this formula is accompanied by a diagram, and the diagram is A and B drawn tail to tail, and theta being the angle between them. We haven't found any usefulness for us to say that theta points from B to A or from A to B. We haven't found anything useful in that. So I usually just try to put it just theta in there and not show an arrow. Occasionally I'll show an arrow just out of habit, but that's really what we're shooting for here is we're trying to just say it's A dot B is equal to A times B times the cosine of the angle between them. So that tells you something. If you learn how to calculate A dot B some other way, then you could actually use A dot B to figure out the angle between two vectors. And I'm going to show you that as an example. But with that being said, I'm also going to tell you that there's another formula for A dot B as well. And that formula is A dot B. If you imagine A is equal to A sub X I hat plus A sub Y J hat plus A sub Z K hat. And if you assume B is similarly defined, B is equal to B sub X I hat plus B sub Y J hat plus B sub, plus B sub Z K hat, then there's another way we can write the dot product. A dot B is also equal to A sub X times B sub X plus A sub Y times B sub Y plus A sub Z times B sub Z. And what that means is I'm just taking the scalar x component of A, multiplying it by the scalar x component of B. I'm multiplying the scalar y component of A times the scalar y component of B, and I'm multiplying the scalar z component of A by the scalar b component or z component of B, and then I'm adding those three multiplication answers together to get a scalar. So that's key because I see repeatedly students do dot products and they give me I hat or J hat in it, and that's not the that's not the way it's supposed to be. When you do a dot product, you're supposed to get a scalar. No I hats are left in it, no J hats, no K hats, no nothing. Okay, so let me show you two vectors, and hopefully this will be enough to give you some idea of some of the tricks we can do with dot products and why they're so helpful. As you might have already noticed, it's obviously helpful in the classification of work when you go to try to calculate work, because what we needed for work was a component of one vector that's parallel to the other vector, either F parallel to D, or like I showed you in that other version I wrote, D parallel to F. Whenever you're trying to find similar components of two vectors, then you use the dot product. Whenever you're trying to find perpendicular components of two vectors, meaning what component is of D vector is perpendicular to F vector. If you're trying to find that, that turns out to be what we call a cross product or also a vector product. So there's a formula for that as well. Now, let me show you a very specific vector. If we imagine going over, let's say 1 unit, and then going up, let's say square root of 3 units, which would be roughly, let's say here. So that's roughly 1.73. Then this vector right here would in fact be at a 60-degree angle, and we'd call that vector A, which equals I hat, because the x component is 1, plus the square root of 3 j hat. That's what vector A is. Now, we could also take, let's say, a vector that is 1, 2, 3. So this would be 3 units here. And actually, I was going to go to the 3, 4, 5 triangle, but I can't. I don't have enough room to draw my 3, 4, 5 triangle. Let's see if I can move this stuff a little bit, and then I can make it a little better. And now I'm going to move this little guy. I'll move that right here. So now I can say I'm going, oops, I wanted that to stick there so I could see it's on the mark. Okay, so each two squares corresponds to 1. So if I want to go up 4, then that would be 1, 1, 2, 3, 4 would be right here. So I could draw my x-axis. Let me move this guy again. Oops. Let me move that guy again and put it over here. And let me continue my y-axis upward. And then this quantity right here would be the number 4. And then I could represent this vector as B. And B is clearly 3 I hat plus 4 j hat, like that. Now, from that, we can say that the magnitude of A is just given by the Pythagorean theorem, which would be 1 squared plus the square root of 3 squared, which is obviously the square root of 1 plus 3, which is the square root of 4, which is 2.000. That's the magnitude of A. We could also do the magnitude of B. The magnitude of B, again, Pythagorean theorem gives us 3 squared plus 4 squared. 3 squared, of course, is 9. 4 squared is 16. If we add 9 to 16, we get 25, and the square root of 25 is 5.000. So there's our magnitudes of our two vectors. Now let's calculate A dot B. So A dot B is supposed to be the magnitude of A times the magnitude of B times the cosine of the angle between them. And it's also supposed to be A sub X, B sub X plus A sub Y, B sub Y plus A sub Z, B sub Z. Neither one of these vectors have Z components, so we're just going to leave that last term off, and that's okay. It's perfectly fine to have a 0 component. So we're going to use the second version. Specifically, we're going to use this is equal to that. So with that in mind, I'm going to say A dot B is equal to A sub X, which is 1, times B sub X, which is 3, plus A sub Y, which is the square root of 3, times B sub Y, which is 4. So we get 3 plus 4 times the square root of 3 is really what the answer is. So A dot B is 3 plus 4 square root of 3. And if you wanted to know roughly what that is, we could just say 4 times the square root of 3. Square root of 3 is about 1.73. So I'll say 3 to the 0.5 power. That's 1.732 roughly. I'm going to multiply that by 4. That gives me 6.928. And now I'm going to add to that 3. And that gives me 9.928 roughly. So this is approximately 9.9. 9.928 is approximately what A dot B is. Now, what I was telling you about is one of the things we can do to actually make use of the dot product is we can use the dot product to find the angle that exists between two vectors. So, for instance, we already knew that the A vector was at an angle of 60 degrees above the horizontal axis. And hopefully you knew that the 3, 4, 5 triangle, which is what the blue one is, that 3, 4, 5 triangle has the angle as the inverse tangent of 4 divided by 3, which is the 53.13. So this angle right here, I'll write it in blue. This angle right here is 53.13 degrees. So if the purple vector is up at 60 degrees and the blue vector is up at 53.13 degrees, what's the angle between them? Anybody? Or can anybody tell me what math we would do to find the angle between them? No answers? So the A vector is at 60 degrees and this vector is at 53.13. So 60 minus 53.13 would make us believe that the angle between these two vectors, theta, is about 6.87 degrees. That's what we believe. Now, I'm going to use the dot product to find out what that angle is, and we'll see if we like it. So what we know is A dot B is 9.928, but what we also know is that A dot B is also equal to the magnitude of A, which is 2.000 times the magnitude of B, which is 5.000 times the cosine of the angle between them, which is theta. So A dot B is actually equal to 10.00 times the cosine theta. So A dot B equals A dot B gives us the following. The first A dot B is 9.928 and the second A dot B is 10.00 times the cosine theta. So theta should be equal to the inverse cosine of 9.928 divided by 10.00. And when I take that, I'm going to say cosine inverse, shift cosine inverse, parenthesis 9.928 divided by 10, close parenthesis, and this gives me 6.880 degrees. Now, we measured it to be about 6.87, but that was using 4 sig figs for the 53.13 and 4 sig figs for the 60 degrees. We only used really 3 sig figs here, so it's not necessarily fair to expect any more than 3 sig figs. So that's why it's off a little bit in the third decimal or in the second decimal place. But that does show us that basically we did get the right angle. So anybody have any questions on that about how to compute a dot product? Okay. So for instance, one of the other things I told you that dot products are for is for finding components of vectors that are parallel to other vectors. So for instance, we know the x component of b, for instance, is 3. If we took a dot product of b with I hat, then what do we get? So let's see that. Let's say I'm going to do this in blue because this is a totally different type of example, but it's a new example still. So I'm going to say this. What is, oops, what is B dot I hat. Okay, as I told you, I'm arguing that a dot product gives you the component of one vector parallel to another. So if I take B dot I, I'm going to say B dot I hat is equal to, now the one of the formulas is B sub x I hat sub x plus B sub y I hat sub y plus B sub z I hat sub z. So we'll use that. And of course, we know the x component of B is, of course, 3. The x component of I hat is 1. The y component of B is 4. But the y component of I hat is 0. And the y component or the z component of B is 0, and the z component of I hat is also 0. So we get just plain 3, which again, as I told you, the 3 is the component of B parallel to I. So uh, 3 is the component of B that is parallel to I hat. And that's what I meant by that. Now, if you actually want to use it that way, then taking the dot product with unit vectors is the best thing because it'll automatically spit out exactly what you want. Otherwise, you have to use something like the projection vector or something like that, which you'll learn about in linear algebra, but you can make it up at any time as well. So basically, it's going to be like a dot B over the magnitude of B squared times B hat or some weird thing like that. But there's neat formulas you can use and make them up. You can look at any of my old videos and I discuss that a little bit, but this is enough for going on right now for doing dot products. Remember, you're going to run into some dot products in the practice tests as well as in your homeworks. You need to do that. Your book does give you some more information. For instance, dot products, if you say I hat dot I hat, since the dot product is written as A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. And of course, remember that always comes with a diagram. So there's A, there's theta, there's B. So I hat dot I hat would be 1 times 1 times the cosine of 0, which is just 1. Similarly, j hat dot j hat is equal to 1 times cosine 0, which equals 1. And k hat dot k hat is equal to 1 times cosine 0 degrees, which equals 1. So we see I hat dot I hat, j hat dot j hat, and k hat dot k hat is all equal to 1. If you go off the beaten path a little bit and do I hat dot j hat, then you get 1 times the cosine of 90 degrees, which equals 0. If you do I hat dot k hat, then that's going to be 1 times cosine 90 degrees, which again is 0. And if you do j hat dot k hat, you get 1 times cosine 90 degrees, which again is 0. Not only that, you can see that I hat dot j hat is also equal to j hat dot I hat, and I hat dot k hat is equal to k hat dot I hat. And finally, j hat dot k hat is equal to k hat dot j hat, and all of that should be just obvious from the fact that the a dot b is a times b times cosine theta, and the order of multiplication doesn't matter. So a times b is the same thing as b times a, and the angle is not going to change just because you multiplied one way in one case and the other way in the other case. So you can see that I hat dot j hat is equal to j hat dot I hat and all that good stuff. So not only that, that gives us yet another way to actually multiply vectors. We already learned AB cosine theta and I already showed you the components of it. But now let me show you why A dot B was equal to AX BX plus AY BY plus AZ BZ. If we said A is equal to AXI hat plus AYJ hat plus AZ K hat, and we took a dot product of that with BXI hat plus BYJ hat plus BZK hat, then we would use our distributive property and we'd say AXI hat dotted with BXI hat plus AXI hat dotted with BYJ hat. That's for this one. Plus AXI hat dot BZK hat. That's for this one. And then we continue on. We'll have to do the AY next. So we could do this one, and this one. And that's going to give you AYJ hat dotted with BXI hat plus AYJ hat dotted with BYJ hat plus AYJ hat dotted with BZK hat. That takes care of those. And now all we have to do is the AZ component like this. So we're just doing distributive property again. So we're going to say plus, and I shouldn't have wrote it equals here because this is just a continuance of the previous line, plus AZ K hat dotted with BXI hat plus AZ K hat dotted with BYJ hat plus AZK hat dotted with BZK hat. Now what we can use is the fact that the dot product is what we call a linear operator, and because of that you're allowed to pull out all the scalar parts out in front of the dot product and just leave the dot product acting on the vectors themselves. So that first term becomes AXBXI hat dot I hat, and that second term becomes AXBYI hat dot J hat. That third one becomes AXBZI hat dot K hat, plus the next term, which is the fourth, would be AYBX, and that's J hat dot I hat, and then AYBY hat dot J hat, plus AYBZ J hat dot K hat, and then continuing on I've got AZBX K hat dot I hat plus AZBY K hat dot J hat plus AZ BZ K hat dot K hat, and we just learned that whenever you take a dot product between two unit vectors, it's either going to be 0 or 1. It's 1 when they're the same, and it's 0 when they're different. So the first term becomes AX BX times 1. The second term becomes 0. The third term becomes 0. The fourth term becomes 0. The fifth term, however, becomes 1, 2, 3, 4, 5. The fifth term becomes A Y B Y times 1. And then the sixth term is 0. And the seventh term is 0. And the eighth term is 0. And the ninth term is AZBZ times 1. So we get AXBX plus AYBY plus AZBY BZ, and that's where we were actually able to find the formula. AB cosine theta is also equal to AX BX plus AY or plus BY AY BY plus AZ BZ. Any questions on that? All right, so in conclusion, what this allows us to do, since we said work is equal to F parallel times D, which would also be D parallel times F, which would also be F times D times cosine theta, then it's obvious that work could be written as F dot D for a constant force. If the force changes anywhere along the path, or changes direction or magnitudes anywhere along the path, then we can't use this formula. So there's got to be a better formula. But you can see now the dot product makes it work really well. And in fact, the only thing we have to do to make it more general is we have to imagine if we're going along a path like this, then you can imagine the d vector, the displacement, which is supposed to be from the beginning to the end. You can imagine breaking it up into little d vectors like this, so that each little d vector is so small that the force doesn't have the ability to change significantly from the left end or the tail end of the d vector to the head end of the d vector. By doing that, you've broken it up into smaller and smaller parts, and then hopefully your force at each point will always be roughly the same from the head to the tail, and then all you have to do is add the individual contributions from each of these, and what that turns out to be is work is equal to the integral of F dot dl, because what we're going to do is imagine these vectors d vectors breaking up into individual components dl vector. So that is a new formula that we have for work in general, and this is a path integral. This is a line or path integral. But the good news is the way we normally use it, you don't even have to know most of the time that it's a path or a line integral. You can just integrate it and it's always going to work out right. That being said, it would be much better if you learned that it's a path integral. That's why I try to teach it as we go. So when I do these integrals, I'll explain to you how to use them. But the main thing is when we go to use them, you have to remember it's a line integral and there's certain rules that you have to use. Whenever you're doing an integral that's, like a line integral, or you'll hear later we're going to do a surface integral or something like that, then what that means is you got to take the integrand, that the thing that you're integrating, and you have to evaluate it on that path or on that line for a line integral. Or if you're doing a surface integral, then you have to basically take the x, y, z values that might be in the integrand and set them equal to something that makes it set on that surface. So that's the difference. And then there's a little rule like when you're using a path integral, you either need to choose that you integrate in the direction of the direction that you're integrating. So you take, the limits of integration and say the bottom limit is the starting position and the top limit is the ending position. And then that indicates which direction you're going. If you're doing that, then the DL just has to point in the positive coordinate direction. Or you can alternatively allow the DL to point the direction that you're going, and then the limits of integration just go from small variable to large variable. I'll explain that with integrals later on. But now that we have this this new definition of work, let me show you something called the work energy theorem. So here is the work energy theorem. calculate the net work. Okay. So to calculate that, I just finished teaching you that the net work is the sum of all the forces acting on this, or the sum of all the works that are done to a particular object. Or we could alternatively say it's the net force dotted with, or as we said before, it'd be times the component of D that's parallel to F or whatever. So we can do the same thing here. We can say W net is equal to the integral of F net dotted with dl. Well, from Newton's second law, the summation of the forces is equal to mass times acceleration, which also equals mass times dv dt, something like that, where this is F net. In other words, F net is the same thing as the left-hand side of Newton's second law. So I can go ahead and plug in the summation of the forces, and then I'm going to dot that with the dl. Well, since it's equal to the left-hand side of Newton's second law, it's also equal to the right-hand side of Newton's second law. So I can write instead the integral of m dv dt dotted with dl, like that. Now, you're probably like me. When I took calculus, I said, well, this is really nice. You know, dy over dx is the symbol we use for the derivative of y with respect to x. And that was just a symbol, and that's the way I treated it. Well, it turns out that dy and that dx are separate things themselves. They're called one forms, or essentially like a one form. And because of that, you can actually manipulate them. You can move them left, right, up, down, and stuff like that. So what I'm going to do is I'm going to replace the dv with the dl and replace the dl with a dv. So in this case, I now get the integral of m dl dt dotted with dv, like that. So now I have the net work done is equal to the integral of m dl dt dotted with dv, a differential velocity element. Can anybody tell me what dl dt is? Think of units if you're having any difficulty. What units would dl dt have, and then what do those units suggest that dl dt is?
Is it acceleration?
Very close. It's dl over dt, so it's meters per second, not meters per second per second. So do you want to reconsider your answer? It's okay. No one ever gets it, but I want to let you know. DLDT has units of meters per second, and in fact, it is the more general definition than, we called it dx/dt was the velocity, but that was actually just the velocity in the x direction. dy/dt was the velocity in the y direction. dz/dt would be the velocity in the z direction, but dl/dt in general is just the velocity. So what we have here is the integral of mv dot dv. Well, dv and v are obviously parallel to each other, so you don't have to worry about the dot product anymore. You can go ahead and write this as the integral of mv dv. And of course, the m is a constant. We can pull that out in front, and you get the integral of v dv. And of course, the integral of v dv is 1/2 v squared. So what we get is 1/2 mv squared, and specifically, we're supposed to integrate it from v initial to v final. So now what we found is w net is equal to 1/2 mv final squared minus 1/2 mv initial squared. And in fact, that is defined to be the change in kinetic energy, K. So that's our work energy theorem. It says the net work done in any process is always, always, always equal to the change in kinetic energy, and kinetic energy is defined to be 1/2 mv squared. That's going to be true for all of regular Newtonian physics. It turns out, however, once you start getting near the speed of light, 1/2 mv squared is no longer the right formula for kinetic energy. But you don't have to worry about that until you start covering relativity or quantum mechanics or something going really, really fast. Okay. So that's two big things that you need to know. The work energy theorem says the total work done in any process is equal to the change in kinetic energy. And as we said with the hiker, we were supposed to assume that the hiker walked up and didn't accelerate, so that more or less they were going so infinitesimally slow that their speed at the beginning was exactly equal to their speed at the end. And you might even call that speed zero. Therefore, we got the total work was zero, which is exactly what we discovered here. And that was zero because the change in kinetic energy was zero. And the work energy theorem tells us that when the change in kinetic energy is zero, then the W net is zero. Any questions on that? All right, so let's look at spring force. So there turns out to be a law called Hooke's law, and Hooke's law actually applies to more than just springs, but we use it for springs. And the main reason why is for from a laboratory perspective, if you wanted to actually measure and use Hooke's law on, let's say, a piece of PVC pipe or a piece of 2x4 or a piece of rebar or something like that, work or excuse me, force is equal to K times X tells you that basically if you apply a force F to an object to like compress it or to stretch it, then the change in the length of that object is going to be given by X, where F is equal to K times X. So if you actually apply a force to stretch it, then that's going to cause the thing to stretch by an amount x given by F divided by K, where K is some property of the material. But you can imagine if you wanted to actually put a large enough force on even a piece of PVC pipe, much less a 2x4 or a piece of steel rebar, if you're actually wanting to put a force on that big enough to see it compress or stretch, then it's going to have to be a huge force, and that means there's a little danger in it. So it's better not to be messing with F equals kx if we're talking about solid, rigid objects. It's better to work with springs that happen to obey the same law and obey it over a much larger range. It turns out that when you actually apply a force on something like that to stretch it, you only have a limited amount of stretch before it's irreparable, because what normally happens is you pull it a little bit, it stretches, and then if you let it go, it goes back to the original size. If you pull it a little bit more, a little bit harder, it stretches a little bit bigger, but then it goes back. But you can reach its elastic limit, at which point when you pull it apart, it actually would throttle or neck down and more or less be ruined, and it's no longer as elastic as it used to be. There's a range of elasticity where F equals kx is valid, and beyond that, it's not valid at all. So what we try to do when we engineer things and we use things like Hooke's law, F equals kx, we try to make sure we stay within the elastic range, and we design all the forces and the sizes of the things that we're using to make sure that they don't stretch too much or compress too much, so that they're no longer linear, so that F is still F equals kx. Now, they normally say F equals negative kx, and that's specifically because the force is a vector quantity. And if you put the object in an XY coordinate system and you imagine pulling in the positive X direction, then the X is going to be positive, but the force itself, see, it's you're pulling in the positive direction. The force that the rod applies to you is in the negative direction. So they often say F is equal to negative KX. And that's just to tell you that the force that the object puts up when you change its distance or its length by an amount X is in the exact opposite direction as the force you applied to it. But right here, we're just treating it as F equals Kx or F sub S equals negative Kx. So if we wish to calculate the work done in stretching a spring, because again, it does work with a spring, what we could do is say this: let us calculate the work a person does to stretch or compress a spring from its normal unstretched length, x sub a equals 0, to an extra length, xb equals x. We assume the stretching is done slowly so that the acceleration is essentially 0. The force Fp is exerted parallel to the axis of the spring along the x-axis, so that Fp and dl are parallel. Hence, dl is equal to dx I hat in this case. What they're saying specifically when we do this, work equals the integral of F dot dl. So let me cordon off this for a second. When we say work is equal to the integral, whoa, Nelly. When we say work is equal to the integral of F dot dl, what we're assuming here is F is equal to F sub x I hat plus F sub y j hat plus F sub z k hat, and then dl is equal to some dx I hat plus some dy j hat plus some dz k hat. That's what really is supposed to go on here. So if we're talking about a spring, let's say we have a spring connected to a wall and sitting over a floor like this, say, then the spring comes out and does this, and then we might say put a x and y axis right here, and if you then apply a force this way to the spring, then the spring is going to stretch an amount x right here, given by F is equal to k times x. So when I go to calculate work equals the integral of F dot dl, I'm going to say that the force is actually, we're going to take, oops, switch to the automatic draw again. We're going to take the integral from x equals 0 to the new x, and the force is going to be kx in the I hat direction. That's the force we actually applied, not the force that the spring is applying to us, because we're going to calculate the work we're doing. And that's going to be dotted with dl, but the y isn't changing, the z isn't changing, so dy and dz are both 0, so we just get dx I hat like that. And of course, I told you that the dot product is what we call a linear operator. So we're allowed to actually take the scalar parts, which is k times x times dx. We're allowed to put that out in front of the dot product and then let the dot product act on the vectors alone, which in this case is I hat dot I hat. And we just learned that I hat dot I hat is 1, so we end up getting the integral from x equals 0 to x of kx dx is actually equal to 1/2 kx squared from 0 to x, which is just 1/2 kx squared. So what we can do is we can treat that as if it's a certain amount of energy stored in a spring that's been compressed, or a certain amount of energy that's stored in a spring that's been stretched, and the amount that it stretched was x, or the amount that it was compressed was x, and therefore we can get it out. So we can say work spring or potential energy, which we use the symbol U. We haven't learned about energy yet, but we are in the next chapter. And this is potential energy because it has the potential to do work. Both of those, we could call it the work done against the spring, the work done by the spring, the potential energy stored in the spring, the potential energy applied to the spring, so on and so forth. All of that is equal to 1/2 kx squared. So this is a whole nother formula that you need to commit to memory because you don't have to do this integral every time. So we can call it work spring equals 1/2 kx squared. But you can also, as you'll see in the next chapter, you can also consider that to be the work done, or excuse me, the potential energy stored in a spring. So let's look at example 7.5, and this should be pretty close to us being about done. Let's say example 7.5. Work done on a spring. A person pulls on the spring in figure 710, stretching at 3 centimeters equals X max, which requires a maximum force of 75 newtons. How much work does the person do? B, if instead the person compresses the spring 3 centimeters, how much work does the person do? So that's the problem. Let me write down what we learned. What we learned was that X max is equal to 3.0 centimeters, and the force required, F max, is equal to 75 newtons. And what we want to know is how much work does the person do? A, the work equals question mark for stretching. So we're trying to figure out how much work is done in stretching it that 3 centimeters by that. And then part B, instead, the person compresses the string by 3 centimeters, how much work is done. So in this case, we want to know work equals question mark for compressing the spring. So that's what we're trying to do. Solution. I want to remind you that Hooke's law actually says that the force is equal to negative kx, but we often just use F is equal to kx. If you're actually plugging it into like Newton's second law to solve Newton's second law, then yeah, you should probably put in the negative. But if you're just calculating the magnitudes, most of the time I just throw the negative away. Now, the other thing we're going to make use of is the fact that the work done in either compressing or stretching is 1/2 kx squared. So we can use any of those formulas. For starters, for part A, though, we're told that the force was equal to 75 newtons and that the stretch resulting from it was 3 centimeters. So F equals kx, because we only care about the magnitude right now, gives us that 75 newtons is equal to K times, and yes, you should be using the base SI units, which is the kilogram for mass, the meter for length, the second for time. And in this case, that means we're going to write 0.030 meters is X. And that means that K is in fact 75 newtons divided by 0.030 meters, and 0.03 is 3 divided by 100, so we're actually multiplying 75 by 100, and then that'll be 7,500, and then we're dividing it by 3, so that'll be 2,500 newtons per meter, and this K is called the spring constant. And it has units of newtons per meter, and that's a typical value, as you might imagine. But you'll see that in labs and stuff like that. So that's F equals kx. Now we have the K, so now we can go ahead and calculate the answer for part A. Specifically, they wanted to know how much work is done. How much work does a person do in stretching it? And that's 1/2 kx squared, which equals 1/2 times 2,500 newtons per meter times, now we're going to take 0.030 meters and we're going to square that. So we're going to take point 0.5 times 2500 times 0.03 squared, and that gives me 1.125 joules is the work done stretching. And I just subscript that stretching to let you know. Of course, we only had 2 sig figs, so the 2 and the 5 are not sig figs, but that's part A. Part B, they want us to do it for compressing, and it's the same formula, and the fact that it's squared means that even if you wrote the compression as negative 3.0 centimeters, when you square it, it's still going to become positive. So that's what's going on here. We can say work is equal to 1/2 kx squared, which equals 1/2 2500 newtons per meter times negative 0.030 meters. That quantity is going to be squared, and lo and behold, we're still going to get 1.125 joules equals W compress. Any questions on that problem? Okay. Now they do a slightly more complicated, but still really pretty trivial example here. This is example 7.6, force as a function of x. So example, I hate it when it keeps doing this. Example 7.6. It says a robot arm controls the position of a video camera, figure 712, in an automated surveillance system is manipulated by a motor that exerts a force on the arm. Assume that the force is given by F of x is equal to some F0, which is a constant, times 1 plus 1/6, another constant, x squared over x0 squared, which is yet another constant like that, where F0 is equal to 2.0 newtons and x0 is equal to 0.0070 meters. And in this case, x is the position of the arm. If the arm moves from x1 equals 0.010 meters to x2 equals 0.050 meters, what we want to know is how much work did the motor do. So W equals question mark. That's what we're trying to calculate. Solution requires us to know the more formal and full definition of work. Work is equal to the integral of F dot dl. So in this case, the fact that it was called F sub x and it's a function of x tells you that the force is probably in one dimension and specifically points in the x direction. So we're going to write this as the integral from x1 to x2 of F of x I hat dotted with dx I hat. That's really what's going on, even though your book consistently skips this because they don't want to make it too nasty or whatever, but it's really not that nasty. We're just going to say the integral from x1 to x2 of f of x dx, like that. It turns out when you're always going from a low coordinate to a high coordinate, like 0.01 to 0.05, then that means you're going in the positive x direction. So if you indicate the direction of the integration by using your dl, that's going to point in the positive direction. But then the limits of integration by default are supposed to point from low coordinate to high coordinate, so they're also going to be in the positive direction. So you don't even have to really know that it's even a line or a path integral, because it just turns out that by going in the positive coordinate directions, both of the sets of variables have exactly the same directions and everything, so it doesn't matter which one you chose. That's why you consistently can get the right answer for most of the problems they do in here. As we get to more difficult problems, I'll show you more complications regarding the line slash path integral. So in this case, we're going to say the work is equal to integral from x1 to x2 of f sub 0 1 plus 1/6 x squared over x0 squared, like that, times dx. Now, we can pull that f0 out in front, integrate from x1 to x2, and in this case, it's going to be, I'll put a curly bracket here, it's going to be the integral of dx, that's for the term being 1, and then plus 1 over 6 x0 squared, that comes out in front, again the integral from x1 to x2, but this time we've already pulled the 6 out in front and the x0 in the denominator squared out in front, and that gives us x squared dx, like that, and then I close my curly brackets. This gives me f0, and then of course the integral of dx is just x, and then we evaluated it at x2 and then minus evaluated it at x1, so this one becomes x2 minus x1 for the first integral, and then 1 over 6 x0 squared, and then the integral of x squared dx is 1/3 x cubed, so that's going to make it 1/3 x2 cubed minus 1/3 x1 cubed. So I went ahead and evaluated it at the limits of integration, and now we can say that it is f0 times x2 was 0.050 meters minus 0.0, no, that's supposed to be 10 there, 0.10 meters. And then plus, we've got 1 over 6, but I also have a 1/3, so I'm going to go ahead and make it 1 over 18. And then x0 we found was 0.007. And that quantity is going to be squared in the bottom. So that's our denominator. And I pulled the 1/3 out in front. So now that's going to be 0.050 meters quantity squared minus 0.010 meters quantity squared. And there's a square bracket in there as well. I didn't necessarily draw it, but we can see. Now I can put in the 2.0 newtons for the F0, the 0.040 meters for the first problem, and then if I take 1 divided by parenthesis 18 times 0.007 squared in parentheses, that gives me, a really big number. That's 1,134, and that is meters to the negative 2 power. That's just the multiplier in front of the square brackets, and then 0.05 squared is 0.0025, and then 0.01 squared. So 0.05 squared minus 0.01 squared is 0.0024, and of course that gives you units of meters squared, like that. Or excuse me, that should have been cubed. Yeah, that should have been cubed. I wrote it as squared. Let me correct that real quick. That's supposed to be a cubed, and I'll give myself a little bit more room over here this time. So this is 0.05 meters cubed minus 0.010 meters cubed, square bracket, curly bracket. Now I still have the 1.134, but the 0.0024 is complete crap. So 0.05 cubed minus 0.01 cubed gives me 0.0001240 meters cubed, like that. And that's now meters cubed over meters squared, which just gives you meters, which is good because we have to add that to 0.04 meters, and we couldn't add that unless it was those units. So now I'm going to take the 0.000124. I'm going to multiply that by 1,134, and that's going to give us 2.0 newtons times 0.040 meters plus, now when I multiply that 1,134 times the 0.0001240, I got 0.1406 meters. Now I'm going to add that to plus zero point zero 0.04, and that gives me 1 point, or excuse me, that gives me 0.1806, 0.1806 meters, and then multiplied that by 2, and that gives me 3.612, or 0.3612 joules. That's the actual answer that we're supposed to get. And hopefully you recognize from your understanding of calculus that that would in fact be the area under the curve of a f versus x graph, where this is x1 and this is x2 and this is f of x. Any questions on that one? Now I actually had 2 extra sig figs here, so I'll underline them to make sure. Anybody have any questions on that one? All right, so we've basically completed chapter 7. There is a nice little example, 7.7, and I'd have 4 minutes, so let me try to fit that example in real quick, and then I'll let you guys go. So example 7.7 says kinetic energy and work done on a baseball. A 145-gram baseball is thrown so that it acquires a speed of 25 meters per second. What is its kinetic energy? Part A. And then part B, what was the net work done on the ball to make it reach the speed if it started from rest? So we have M is equal to 0.145 kilograms. I went ahead and converted that to kilograms. We have V initial is equal to 0 meters per second. We have V final is equal to 25 meters per second. And we're asked A, K final is equal to question mark. And then B, what was the net work done? W net equals question mark. Our solution is, we first have to understand that K is defined to be 1/2 mv squared. And we also need the work energy principle, which says that the W net is equal to the change in kinetic energy, which equals 1/2 mv final squared minus V initial squared, like that. So let's start off with part A. The kinetic energy is equal to 1/2 times 0.145 kilograms times 25 meters per second, quantity squared. That gives me 0.5 times 0.145 times 25 squared, gives me 45.31 joules. Notice kilograms times meter squared per second squared. A kilogram meter per second squared is a Newton, so a kilogram meter squared per second squared is a Newton meter, and that's a joule. So this is equal to kinetic energy. So we've done part A, and then part B, the change in kinetic energy, delta K, which equals K final minus K initial, which equals 45.31. And we actually only had 2 sig figs, so I have to underline that. That's 45.31 joules minus 0 joules because the initial velocity is 0 and 1/2 m times 0 squared is 0. But we also know that that is equal to W net. So we now say that W net is also equal to 45.31 joules. That's what the work energy theorem is about. You can also use it, and this is the more common example, they use it to calculate the speed during a collision because you know that the friction force would do work against the car, and that friction force is force, or that work done by friction force would be the friction force times the distance of the skid mark. So that would be seen as the work net. And then that's equal to kinetic energy, which actually, by the way, that work net would come out negative because the friction force is pointing one way while the car is going the other way. So you would expect that to be a negative amount of work done. So you get a negative amount of work is W net, and that's equal to 1/2 mv final squared, which v final is 0 because you just get it to a stop, minus 1/2 mv initial squared, which is not 0, and therefore you can go ahead and solve for that by saying that W net is equal to negative the friction force times the distance, which is equal to 1/2 mv final squared minus 1/2 mv initial squared, but v final squared is 0, so we get that negative FD is negative 1/2 mv initial squared, so V initial would equal 2FD over M square root. And that's the typical way that we can go about trying to estimate what the total work done against friction is, and also what the initial speed was in a car wreck. So we're done here. I'll wait till the last person leaves in case anybody has any questions. Remember, you have a face-to-face test and an online test that's due on the 29th. The face-to-face test will be available for you Saturday morning as early as you want, long as it's Saturday, and available to you until anytime Sunday evening up till midnight, at which time you're supposed to be finished with it. So, or excuse me, Monday night, not Sunday. So you have Saturday or Sunday or Monday that you can take it, and you got to have it done by then. But you also have the online test that's due by then as well. Doing the practice test for the online test turns out to be the same practice test for the face-to-face test, so you're practicing all that. So you've got 2 tests. Don't miss them. You're not doing them in the lab. Have a nice weekend, and good luck on your test. That's it. Well, thanks for coming, everyone, and hope to see you this time next week. Talk to you later. Bye-bye.